Here we have a second example of a common physics device, and we're going to look at how we know this is in simple harmonic motion and get an expression for the period of oscillation of our object, just like we did for the mass on a spring previously. So here we have a simple pendulum, length L from the center of mass of the bob to the point of suspension. I'm calling the tension in the string here S to avoid confusion with the period T. The mass of the bob M then produces a weight mg due to gravity. And here we have the bob displaced at some point in its oscillation to an angle theta with the vertical. So I've also got the length y of the arc made here, which is going to be important a little later on in what we're doing. So let's first get an expression for the force which is causing the bob to accelerate. And what we're going to do is to resolve our forces, of which there are only two, the tension and the weight. We're going to resolve those along the string and at right angles to the string. We could resolve horizontally and vertically. I'm choosing to resolve parallel to the string and perpendicular to it. So let's resolve our forces in those directions and see what comes of that. So along the string, we have the tension here, and if you think about your geometry, here is a vertical line cutting through the direction of the string. So this angle here is also theta. So the component of the weight along the string will be mg cos theta. So we have mg cos theta equals the tension S. So if we then carry on and resolve at right angles to the string, well, here we have mg sine theta. There are no other forces in that direction. The tension acts along the string, so there is no component at right angles to it. So we only have mg sine theta. So this is the resultant force in that direction at right angles to the string. And by Newton's second law, then, mg sine theta equals ma. So we're getting somewhere now. We have the force which causes the acceleration. So clearly g sine theta equals a. It's not looking very like simple harmonic motion right now, is it? Because although g is a constant, we have a proportional to sine theta, and we need a proportional to the displacement. So if we go back and we look at this distance y, we can say that as long as theta is small, and here we have a really important condition for the simple pendulum, as long as theta is small, then sine theta and theta are going to be the same value if you take theta in radians. That's important. So if theta is 10 to 15 degrees or less, then sine theta is approximately equal to theta if theta is in radians. That is really important. So our expression then becomes A equals g theta. in those circumstances. So in the situation where we have a small angle of displacement from the vertical, then with theta in radians, theta and sine theta have the same value. Check that. Calculate the value of 10 degrees in radians. Take the sine of that, making sure your calculator is in radians, and you'll find that the two are the same. So let's then go back and look at our arc y. We know that if theta is in radians, the length of the arc is r theta, and here the length of the circle, sorry, the length of the radius of the circle that this arc is a part of is L, here, length of the pendulum L. So we have, sorry, we have theta is y over L. So now we're going to stick y over L in here, and we're going to have A is gy over L. So now we can see g and L are constants, so A is proportional to y. And of course, if we go back to our diagram, when y is to the left, the acceleration is this way, because that's the direction of the force, the resultant force that we calculated. And when y is to the right, A is, again, towards the center, because the resultant force is towards the center. So we have A is minus some constant times y, which of course is our definition of simple harmonic motion. So here we have demonstrated, proven, that as long as the angle is small, then the bob will perform simple harmonic motion. So, as we did with the mass on a spring, we can see here that K has to equal omega squared, because that's what simple harmonic motion says, which means, of course, that G over L is omega squared. So omega then is the square root of G over L. And since period is 2 pi over omega, we stick that in there. Then we have the expression, the period of a simple pendulum is 2 pi L over G. And of course, that only applies when the angle is small. You're likely to be asked, under what conditions does a simple pendulum perform simple harmonic motion? And that is the condition, small angle.